The information provided in this video is for educational and entertainment purposes only. Automotive repair involves inherent risks including, but not limited to, physical injury, property damage, and exposure to hazardous materials such as caustic chemicals, high-pressure fluids, and heavy machinery. This content does not constitute professional mechanical advice, legal guidance regarding vehicle warranties, or a certification of safety. Every vehicle is different, and you should always consult your specific vehicle's factory service manual and follow all manufacturer-recommended safety protocols. The creator of this content is not responsible for any damage to property or injury to persons resulting from the use or misuse of the information presented. Always wear appropriate personal protective equipment and work in a ventilated, well-lit environment. Conduct your own due diligence and work within the limits of your own skill and comfort level. Did you know that the average American driver is currently spending nearly $10,000 a year just to own and operate their vehicle? A massive portion of that cost is swallowed up by a black hole of repair bills and maintenance fees that most people simply accept as an unavoidable tax on modern life. Imagine you are driving down the highway and a small, amber light flickers on your dashboard. For most, that light is not just a warning. It is a symbol of impending financial doom. You take it to a dealership, and within 20 minutes, a man in a clean polo shirt tells you that you need a $3,000 catalytic converter replacement, a $400 fuel induction service, and a complete cooling system flush. You feel trapped. You feel like a victim of a machine you do not understand. But here is the reality. That light might be triggered by a loose gas cap or a $15 oxygen sensor that you can replace in your driveway in 10 minutes using a tool that costs less than a fast food meal. There is a massive knowledge gap between the person behind the steering wheel and the person under the hood, and that gap is costing you thousands of dollars in lost potential savings every single year. We are entering an era where the right to repair is being challenged by complex software and proprietary parts. Yet the fundamental physics of the internal combustion engine remain the same as they were 50 years ago. Today, we are opening the hood on the industry itself. We are going to deconstruct the fear that keeps you from touching your own engine and replace it with a systematic, professional-grade understanding of how your vehicle actually functions. This video is the first step in a complete transformation. By the time we finish this masterclass series, the mystery of the machine will be gone. You will understand the language of your car, the economics of the repair shop, and the physical skills required to maintain your most expensive mobile asset. This is about more than just changing oil, it is about reclaiming your autonomy. We are going to look at historical trends in vehicle reliability and analyze case studies of how simple maintenance neglect leads to catastrophic engine failure. You are going to learn how to diagnose problems before they become emergencies, how to source parts without the massive dealership markup, and how to build a professional-grade toolkit on a budget that makes sense for a beginner. This is your guide to stopping the bleed of your bank account and taking total control of your automotive journey. To understand where we are going, we have to understand the current state of the automotive industry. In the United States, the average labor rate at a dealership now hovers between $150 and $250 per hour. When you see a mechanic working on your car, you aren't just paying for their time. You are paying for the building's mortgage, the service advisor's commission, and the expensive diagnostic software subscriptions. This is known as the flat rate system. In this system, every job is assigned a specific amount of time by a manufacturer's manual. If a brake job is billed at 3 hours, you pay for 3 hours of labor even if the technician finishes it in 45 minutes. This creates a massive incentive for speed over precision in many high-volume shops. By learning to do these tasks yourself, you are essentially paying yourself that $200 hourly rate. Let us look at a practical case study. The standard brake pad and rotor replacement. A typical shop might quote you $600 to $800 for a single axle. However, the physical parts, high-quality ceramic pads and vented rotors, might only cost $120 from a reputable online wholesaler. The actual process involves removing exactly 5 lug nuts, 2 caliper bolts, and 2 bracket bolts. If you have the knowledge, you can save $500 in an afternoon. That is the potential outcome of mechanical literacy. It is not just about the money, it is about the quality of the work. When you do it yourself, you are the only person who cares enough to clean the rust off the hub surface or properly torque the bolts to factory specifications. The biggest barrier for most beginners is not a lack of intelligence. It is the sheer complexity of the modern engine bay. When you pop the hood of a 2024 SUV, it looks like a plastic-covered labyrinth. This is a psychological tactic used by manufacturers to discourage DIY repair. Underneath those plastic beauty covers, however, is a machine that operates on 4 simple stages: intake, compression, power, and exhaust. Every single component you see serves one of those 4 stages or supports the systems that make them possible, such as cooling or lubrication. To master auto repair, you must learn to see past the plastic and recognize the systems. We must also address the culture of safety, which is the foundation of every professional technician's career. A car weighs anywhere from 3,000 to 6,000 pounds. If it is not supported correctly, it is a lethal object. Beginners often make the mistake of trusting a hydraulic floor jack alone. This is a critical error. Hydraulic seals can and do fail without warning. We will be diving deep into the physics of secondary support systems, why you need jack stands rated for the weight of your vehicle, and why those stands must be placed on reinforced pinch welds or frame rails. We will discuss the shake test, a mandatory safety step where you physically try to knock the car off the stands before you ever put a limb underneath it. If the car moves, your setup is wrong. This level of detail is what separates a hobbyist from a professional. Furthermore, we need to talk about the tools of the trade. Many beginners think they need to spend thousands of dollars at a professional tool truck to get started. This is a myth. In fact, historical trends in the tool industry show that many mid-tier brands now offer tolerances and warranties that rival professional brands at a fraction of the cost. We will analyze the tiered tooling strategy, where you invest in high-quality items for tools that take the most abuse, like ratchets and torque wrenches, while saving money on items like sockets and screwdrivers. You will learn the difference between a chrome socket, which is designed for hand use, and a black phosphate impact socket, which is designed to handle the violent vibrations of a pneumatic or cordless impact wrench. Using the wrong one can lead to shattered metal and high-velocity shrapnel. We are also going to explore the digital side of modern repair. Every car manufactured after 1996 in the US is equipped with an OBD2 port. This is your direct line of communication with the vehicle's computer. We will discuss how to use an inexpensive Bluetooth scanner to pull freeze-frame data. This data shows you exactly what the engine was doing the millisecond that check engine light turned on, how hot the coolant was, how fast the engine was spinning, and whether the fuel mixture was too lean or too rich. Instead of guessing and throwing parts at a problem, you will learn to use data-driven diagnostics to find the root cause. This is how you avoid the parts canon, a common mistake where beginners waste hundreds of dollars replacing components that aren't actually broken. As we move through this series, we will break down the chemistry of fluids, why using the wrong type of coolant can turn into a gelatinous sludge that destroys your radiator, and why modern synthetic oils allow for longer drain intervals but require higher quality filtration. We will look at the tactile side of mechanics, the feel of a bolt reaching its yield point, the sound of a failing wheel bearing that mimics the hum of an airplane, and the smell of burning transmission fluid that signals an internal failure long before a light appears on the dash. Auto repair is a sensory experience, and we are going to tune your senses to the frequency of your machine. This is the start of your journey from a driver to a master of your own mobility. To master your own mobility, you must first master the extension of your hands. Imagine it is a Saturday morning in the spring of 2026. You are standing in your driveway in a suburb of Phoenix, Arizona, looking at a slow rhythmic drip of amber fluid hitting the concrete under your 5-year-old SUV. In 2024, a simple diagnostic fee at a local shop might have cost you $80. In 2026, due to the rising costs of specialized labor and the overhead of advanced diagnostic hardware, that same shop now charges $140 just to tell you where the leak is coming from. This is where the divide begins. You can either call a tow truck and surrender your financial agency, or you can open your toolbox. But here is the problem. Most beginners own a kitchen drawer full of mismatched screwdrivers and a rusty pair of pliers. To operate at a professional level, you need to understand the tooling mindset. This is not about amassing a collection of shiny metal. It is about building a systematic interface between your brain and the machine. Let us look at a case study involving a driver named Alex. Alex owns a 2021 sedan that is officially out of its manufacturer warranty as of this year. Alex noticed a vibration in the steering wheel during braking. A franchise repair shop quoted Alex $950 for a front brake job, citing the high cost of the electronic wear sensors and the labor required to reset the brake system through the vehicle's computer. Alex decided to invest $300 into a foundational tool set instead of paying the bill. This set included a high-quality 3/8-inch drive ratchet, a range of metric sockets, and a digital torque wrench. By spending 4 hours on a Saturday following a factory service manual, Alex completed the job. The potential outcome was not just a savings of $650. It was the acquisition of a tool kit that will last for the next 30 years. Historical trends show that the cost of quality hand tools has remained relatively stable when adjusted for inflation, while the cost of automotive labor has spiked by over 40% in the last 5 years. The first pillar of your masterclass toolkit is the socket set. In the automotive world, the 3/8-inch drive is the workhorse. You need to understand the physics of the drive size. A 1/4-inch drive is for small, delicate interior work or sensors where high torque would snap a bolt. A 1/2-inch drive is for heavy suspension components and lug nuts where you need massive leverage. The 3/8-inch drive is the perfect balance for 80% of the fasteners on your vehicle. When selecting sockets, you must choose 6-point sockets over 12-point sockets. A 12-point socket looks more versatile because it can fit onto a bolt at more angles, but it only makes contact with the very corners of the fastener. In a 2026 vehicle that has seen a few winters in the Rust Belt, those corners are often soft and degraded. A 12-point socket will round off a stuck bolt, turning a 10-minute job into a 3-hour nightmare involving extractors and heat torches. A 6-point socket grips the flat sides of the bolt head, allowing you to apply maximum force without slipping. Next, we address the ratchet itself. In 2026, we have moved beyond the coarse tooth ratchets of the past. Professional technicians now favor high tooth count ratchets, typically 72 to 120 teeth. This matters because of the swing arc. In the cramped engine bay of a modern hybrid or a compact turbocharged car, you might only have 2 inches of space to move your hand. A coarse 36-tooth ratchet requires a 10-degree swing just to click to the next tooth. A 120-tooth ratchet only requires a 3-degree swing. This means you can remove fasteners in tight spots that would be physically impossible to turn with cheaper, older tools. Beyond the ratchet, you must understand the combination wrench. These are your secondary line of defense. A quality wrench should have a box end with a slight offset, allowing you to reach fasteners on a flat surface without scraping your knuckles. We also need to discuss the importance of metallurgy. Cheap tools are often made of cast alloys that can flex or shatter under pressure. Professional-grade tools are forged from chrome vanadium or chrome moly steel. This strength allows the tool walls to be thinner, which is critical when you are trying to fit a wrench into a narrow gap between an alternator and a frame rail. Let us consider another scenario. Imagine you are attempting to change a battery in a 2024 pickup truck. To save space, the manufacturer has tucked the battery deep under the plastic cowl. You cannot reach the hold-down bolt with a standard ratchet. This is where extensions and universal joints become mandatory. A beginner often tries to use a pair of pliers to reach these bolts, which leads to stripped heads and frustration. A professional beginner knows that a 10-inch extension bar and a wobbler socket are the correct keys to that specific lock. This is the difference between working hard and working with mechanical intelligence. We must also discuss the digital side of 2026 auto repair. Every beginner needs a basic OBD2 scan tool. In the past, these were expensive standalone units. Today, you can get a high-speed Bluetooth dongle that plugs into the port under your dash and communicates with your smartphone. When your car enters a limp mode where the engine power is restricted, the computer is trying to tell you exactly what is wrong. By reading the P codes or diagnostic trouble codes, you move from the realm of guessing to the realm of data. If the code is P0302, you know you have a misfire on cylinder number 2. You can then swap the ignition coil from cylinder 2 to cylinder 3. If the code changes to P0303, you have successfully diagnosed a failing coil without spending a single dollar on a part. This systematic approach is the core of the masterclass. Safety gear, often dismissed by hobbyists, is the final element of your foundational setup. You need impact-rated safety glasses because the tension in a rusted bolt can cause it to snap and send a shard of hardened steel toward your face at high velocity. You need nitrile gloves, not just to keep your hands clean, but to protect your skin from used motor oil, which is a known carcinogen containing heavy metals and combustion byproducts. Historical trends in occupational health show that long-term exposure to these fluids can lead to significant health issues, making a 5-cent glove a massive investment in your future. As you stand in your garage in 2026 surrounded by your organized tools, you are no longer just a consumer. You are a technician in training. You have the hardware, the software, and the safety protocols. But having the tools is only half the battle. If you don't know how to safely get that 4,000-pound machine off the ground, the tools are useless. In fact, if you use your jack incorrectly, you aren't just risking a repair, you are risking your life. Most people think they know how to lift a car because they have seen the emergency jack in their trunk, but that jack is a widowmaker designed for one-time emergency use only. Before you ever turn a wrench, you must understand the physics of gravity and the structural integrity of your vehicle's frame. If you place a jack stand on the wrong part of the floor pan, it will punch through the metal like a soda can. If you don't use wheel chocks, the car can roll off the stands the moment you apply torque to a stubborn bolt. Are you ready to learn the 3-point safety check that ensures your car will never move while you are under it? We are about to dive into the high-stakes world of vehicle lifting and stabilization, where the margin for error is zero. This is the transition from preparation to action. Do you know where your vehicle's primary lift points are located? And more importantly, do you know which secondary points are strong enough to save your life if a jack fails? The next step in your journey involves the most dangerous part of auto repair, and mastering it is the only way to move forward safely. We are going under the car. To respect the 4,000 pounds of steel hovering above your head, you must first understand the physics of failure. Imagine a driver named Marcus in 2026. Marcus owns a heavy electric SUV that weighs nearly 6,000 pounds due to the massive battery pack integrated into the chassis. He decides to rotate his tires in his driveway to save the $80 service fee. He pulls out the factory scissor jack, the one that comes with the spare tire, and begins to lift. This is a critical moment. In the industry, we call that scissor jack a widowmaker. It is not designed for maintenance. It is a single-use emergency tool meant only to get a flat tire off the ground on the side of a road. It has a narrow base and zero secondary stabilization. If a gust of wind hits the vehicle or if Marcus leans too hard on a lug nut, the jack can fold like a piece of origami. Historical trends in emergency room data show that a significant percentage of automotive-related injuries occur when individuals use inadequate lifting equipment on unstable surfaces. To operate safely, you must invest in a high-quality hydraulic floor jack and a pair of jack stands. In 2026, the standard for a DIYer should be a 3-ton low-profile floor jack. The low-profile design is essential because modern cars are often designed with aerodynamic side skirts that leave very little clearance. The jack works through Pascal's principle, using hydraulic fluid to multiply the force of your arm into thousands of pounds of lifting power. However, you must never, under any circumstances, place any part of your body under a vehicle supported only by a hydraulic jack. Hydraulics rely on rubber O-rings and pressurized oil. If a seal fails, the car does not descend slowly. It drops at the speed of gravity. This is why jack stands are the non-negotiable insurance of the automotive world. When you select jack stands, you are looking for mechanical locking mechanisms. There are two primary types, the ratchet style and the pin style. The ratchet style uses a serrated bar that locks into place as you raise it, while the pin style uses a heavy steel bolt that passes through the stand. Case studies of shop safety suggest that pin-style stands offer a slightly higher margin of safety against accidental release, but both are light years ahead of a floor jack alone. For a vehicle like Marcus's heavy SUV, he would need stands rated for at least 3 tons each, ensuring that the combined capacity far exceeds the weight of the vehicle. The next challenge is identifying where to actually lift the car. This is where most beginners cause permanent damage. If you place a jack under a floor pan, you will crush the thin sheet metal and potentially damage the interior carpet or even electrical wiring harnesses. If you place it under a suspension arm that is not designed to bear the weight of the car, you can bend it, ruining your alignment and creating a safety hazard. You must locate the factory-designated lift points. On most modern unibody vehicles, these are the pinch welds. These are the reinforced areas where the various panels of the car's frame are welded together, typically located behind the front wheels and in front of the rear wheels. For vehicles with a body-on-frame construction like a Jeep or a full-size truck, you lift directly from the heavy steel frame rails. Let us walk through the step-by-step process of a safe lift. First, you must ensure the vehicle is on a flat, level concrete surface. Never lift a car on asphalt during a hot 2026 summer day. In a state like Florida or Texas, the heat can soften the asphalt, causing the narrow feet of a jack stand to sink into the ground, tilting the car and causing it to fall. Once on concrete, you must engage the parking brake and chock the wheels that will remain on the ground. If you are lifting the front of the car, you place heavy rubber or plastic chocks behind the rear wheels. This prevents the car from rolling, which is the leading cause of a car falling off a jack. Next, you position the floor jack under the lift point and begin to pump the handle. As the car rises, you must watch the jack. Most floor jacks have wheels because they need to roll slightly forward as the lifting arm moves in an arc. If the jack is stuck and cannot roll, it can actually pull the car off the lift point. Once the car is high enough, you slide the jack stand into place under a secondary reinforced point or a different section of the pinch weld. You then slowly, very slowly, turn the handle of the floor jack to lower the vehicle onto the stand. Now comes the most important step for any beginner: the shake test. With the car on the stands and the floor jack slightly lowered but still nearby as a backup, you grab the bumper or the frame and you give the car a significant, firm shake. You are trying to see if there is any movement or instability. If the car moves, your stands are not seated correctly. It is much better for the car to fall while you are standing next to it than while you are underneath it. Potential outcomes of skipping this test include catastrophic injury. A professional technician does not feel confident until the shake test is passed. As a final failsafe, many DIYers take the wheel they have just removed and slide it under the frame of the car near where they are working. If the stands and the jack were to fail simultaneously, the car would land on the wheel and tire, leaving enough of a gap to prevent you from being crushed. This is a layer of redundancy that costs nothing but provides immense peace of mind. Imagine the difference in the experience of Marcus and another driver, Sarah. Sarah follows these protocols in 2026. She uses her 3-ton stands, chocks her wheels, and passes her shake test. When she is under the car, she can focus entirely on the task at hand, inspecting a fuel line or changing a sensor, without the nagging fear that her environment is unstable. She has created a professional-grade workspace in her own garage. But safety isn't just about preventing the car from falling. It is also about the chemistry and the heat that live inside that machine. Now that you are safely under the vehicle, you are going to encounter the lifeblood of the engine: the fluids. Every fluid in your car, from the engine oil to the brake fluid to the coolant, tells a story about the health of the machine. However, if you open the wrong cap at the wrong time, you are dealing with pressurized liquids that can reach temperatures of over 200 degrees Fahrenheit. Do you know why you should never touch a radiator cap when the engine is warm? Or why certain fluids can strip the paint off your car in seconds? Do you know the historical trends of why manufacturers are moving toward lifetime fluids and why that might actually be a case study in planned obsolescence? Now that we are safely under the car, we are going to open the veins of the machine and learn how to perform the most fundamental maintenance task in existence. We are about to dive into the science of lubrication and the critical art of the fluid exchange. The primary fluid that dictates the lifespan of your internal combustion engine is the motor oil. Imagine a driver named David in Chicago during the winter of 2026. David owns a 2020 hybrid SUV with over 80,000 miles on the odometer. Outside, the temperature has dropped to 10 degrees below zero. When David starts his vehicle, the internal combustion engine must roar to life instantly to assist the electric motors. In these first few seconds, the engine oil is thick, cold, and sitting at the bottom of the oil pan. This is the most dangerous moment for any engine. Historical trends in automotive engineering show that approximately 75% of all engine wear occurs during the warm-up period. If David has been using a high-viscosity conventional oil, that fluid might be too thick to move through the narrow oil galleries, leaving the metal components of the engine to grind against each other without protection. To understand why an oil change is the cornerstone of auto repair, you must understand the science of viscosity. Oil is labeled with 2 numbers, such as 0W20 or 5W30. The W stands for winter. The first number represents the oil's flow rate at 0 degrees Fahrenheit, and the second number represents its flow rate at 212 degrees Fahrenheit. In 2026, many modern engines require 0W16 or even 0W8 oil. These are ultra-thin fluids designed to reduce internal friction and maximize fuel economy. By choosing to change his own oil, David ensures that he is using a full synthetic fluid that meets the specific API or ILSAC standards required for his high-tech engine. A potential outcome of using the wrong oil in 2026 is the premature failure of the variable valve timing solenoids, a repair that can cost over $1,000 in labor alone. Let us walk through the physical act of a masterclass oil change. You have already safely lifted the vehicle following the protocols from the previous part. Now you must locate the oil drain plug. This is typically a single large bolt at the lowest point of the engine's oil pan. Before you loosen it, you must place your drain pan directly underneath. A common mistake beginners make is placing the pan directly under the bolt. Because the oil is under pressure from the weight of the fluid above it, it will shoot out in an arc. You must position your pan several inches back to catch the initial stream. When you remove the plug, you must inspect the crush washer. This is a small metal ring, often made of aluminum or copper, that sits between the bolt and the pan. Its job is to deform and create a perfect seal. In a 2026 case study of DIY oil changes gone wrong, over 30% of leaks were traced back to a technician reusing an old flattened crush washer. This is a 3-cent part that saves you from a $50 mess in your driveway. Once the oil has slowed to a very thin drip, you replace the plug and torque it to the factory specification. Over-tightening is a fatal error. Many oil pans are made of soft aluminum, and if you strip the threads, you are looking at a $300 pan replacement. Next is the oil filter. This is the kidney of your engine, trapping carbon, metal shavings, and debris. There are 2 types: the traditional spin-on metal canister and the modern cartridge filter. If you have a spin-on filter, you must perform the gasket check. When you remove the old filter, verify that the rubber O-ring is still attached to it. If that ring sticks to the engine block and you install the new filter on top of it, you have created a double gasket scenario. The moment you start the engine, the high oil pressure will blow out that double seal, and your engine will pump its entire 5-quart oil capacity onto the ground in less than 30 seconds. This leads to immediate engine seizure. Before installing the new filter, take a finger and smear a light coating of fresh oil onto the new rubber gasket. This ensures the gasket does not bunch up or tear as you tighten it. Now, consider the transmission fluid. In 2026, many manufacturers claim their vehicles have lifetime transmission fluid. This is a misleading marketing term. There is no such thing as a lubricant that lasts forever. Historical trends in the used car market show that vehicles with lifetime fluid often experience transmission slippage or total failure shortly after the 100,000-mile mark. A case study from an independent laboratory analyzed lifetime fluid after 60,000 miles and found high concentrations of clutch material and oxidized chemicals. By performing a drain and fill of your transmission fluid, which is often as simple as an oil change, you are potentially extending the life of your transmission by an additional 10 years. While you are under the car, you must also look at the brake fluid. This is a hygroscopic fluid, meaning it actively absorbs moisture from the air. In a humid environment like Miami or Houston, your brake fluid can reach a 3% water content in just 2 years. When you step on the brakes, the friction creates immense heat. If there is water in your brake fluid, that water can turn into steam. Unlike liquid, steam is compressible. This leads to a soft, spongy brake pedal and a significant increase in stopping distance. In 2026, a basic copper strip test can tell you the exact health of your brake fluid. If the test indicates high moisture, a complete flush is necessary to prevent internal corrosion of the ABS pump, a component that costs nearly $2,000 to replace in modern vehicles. The economics of doing this yourself in 2026 are staggering. A high-end synthetic oil change at a dealership now averages between $120 and $160. By purchasing a 5-quart jug of premium synthetic oil for $35 and an OEM filter for $12, you are performing a superior service for less than $50. Over the course of 5 years, assuming 2 oil changes per year, the potential outcome is over $1,000 in direct savings, not including the preventative value of catching other issues while you are under the hood. However, once you have drained the old fluids and replaced them with fresh, high-performance lubricants, you are faced with a new challenge. Your car is no longer just a mechanical object. It is an electronic one. In 2026, every fluid change must be communicated to the vehicle's central nervous system. If you change your oil but do not reset the internal degradation monitor, the car may still operate in a reduced power mode or fail to optimize its fuel mapping. Even more importantly, there is one fluid we haven't touched yet, because it is the most volatile and dangerous system in the entire vehicle. It operates under immense pressure, it can cause third-degree burns in an instant, and it is the only thing keeping your engine from melting into a solid block of useless aluminum. We are talking about the thermal management system. Do you know why modern engines run hotter than they did 20 years ago, and why the wrong color of coolant can literally eat your engine from the inside out? We are moving from the blood of the engine to its cooling system. If you think an oil leak is bad, wait until you see the catastrophic results of a coolant system failure at 70 miles per hour. Are you ready to learn how to pressure test your system and identify the invisible leaks that are currently threatening your engine's survival? The next part of our masterclass dives into the high-pressure world of radiators, water pumps, and the chemistry of heat. The high-pressure environment of your cooling system is the only thing standing between a smooth commute and a catastrophic engine meltdown. Imagine a driver named Jennifer in the summer of 2026, navigating a heat wave in Atlanta. Jennifer is driving a 7-year-old turbocharged sedan. As she sits in bumper-to-bumper traffic, she notices a faint, sweet smell, similar to maple syrup, wafting through the vents. This is not a pleasant aroma. It is the scent of ethylene glycol atomizing as it escapes a pinhole leak in a pressurized hose. In 2026, modern engines are designed to run hotter than ever to maximize fuel efficiency and reduce emissions. While an older vehicle might have operated at 190 degrees Fahrenheit, Jennifer's engine is designed to sit comfortably at 220 degrees. This higher operating temperature means the margin for error is razor thin. If her cooling system loses pressure, the coolant will flash into steam, the cylinder head will warp, and the potential outcome is a $4,000 engine replacement. To master this system, you must understand the chemistry of the fluid. In the past, almost every car used the same green inorganic acid technology coolant. Today, in 2026, the industry has fractured into a rainbow of proprietary chemistries: organic acid technology, hybrid organic acid technology, and phosphate hybrid organic acid technology. These are not interchangeable. If Jennifer were to top off her orange OAT coolant with generic green IAT coolant, the different chemical packages would react, creating a thick, brown sludge. This sludge settles in the narrow passages of the heater core and the radiator, effectively choking the engine to death. Historical trends show that cooling system neglect is the #1 cause of roadside breakdowns in the United States. The heart of this system is the water pump. Think of it as a centrifugal pump that circulates fluid through the engine block and out to the radiator. Most beginners don't realize that water pumps are designed with a built-in warning system called a weep hole. This is a small orifice behind the pump's pulley. When the internal mechanical seal begins to fail, a tiny amount of coolant will leak out of this hole. If you are performing a regular visual inspection and you see crusty, colorful deposits around the water pump, you are looking at a case study in preventative maintenance. By replacing a $60 pump now, you avoid a scenario where the pump seizes, snaps the serpentine belt, and leaves you stranded. Next, we must discuss the thermostat, the gatekeeper of the system. It is a simple mechanical valve filled with a specialized wax. As the engine heats up, the wax expands, pushing the valve open and allowing coolant to flow to the radiator. If a thermostat fails in the closed position, the engine will overheat in minutes because the heat has nowhere to go. If it fails open, the engine will never reach its optimal operating temperature, leading to poor fuel economy and excessive carbon buildup. In 2026, many vehicles have moved to electronically controlled thermostats that the car's computer can manipulate based on driving conditions. Diagnosing these requires the OBD2 skills we discussed earlier. Let us walk through the process of a cooling system pressure test, which is the professional way to find invisible leaks. You don't need the engine running for this. You use a specialized hand pump that attaches to the radiator neck or the coolant expansion tank. You pump the system up to the pressure listed on your radiator cap, usually around 15 to 20 pounds per square inch. With the system under pressure but the engine cold and silent, you can listen for the hiss of escaping air or watch for the drip of fluid. This is how you find a hairline crack in a plastic radiator side tank that only opens up when the car is at full operating temperature. When it comes time to perform a coolant flush, the biggest challenge for a beginner is not draining the fluid, but getting the air back out. This is known as burping the system. Air is a poor conductor of heat. If an air bubble gets trapped in the cylinder head, that specific spot will overheat, even if your temperature gauge looks normal. To prevent this, professionals in 2026 use a spill-proof funnel that attaches to the highest point of the cooling system. You fill the funnel, start the engine, and watch as the air bubbles rise to the top while the fluid takes their place. Some modern vehicles even require a vacuum fill tool, which sucks all the air out of the system to create a vacuum before drawing the new coolant in. This ensures there are zero air pockets in the complex cooling jackets of a modern engine. The economics of maintaining your cooling system are undeniable. A professional coolant flush in 2026 can cost upwards of $250. You can perform the same service for the cost of 2 gallons of concentrated coolant and a gallon of distilled water, totaling about $40. But the real value is in the longevity of the components. Over time, coolant becomes acidic. This leads to a process called electrolysis, where the fluid actually starts to carry an electrical charge, eating away at the aluminum of your engine from the inside out. By testing your coolant's pH level and changing it every 5 years or 50,000 miles, you are protecting the structural integrity of the entire powertrain. Imagine if Jennifer had known these steps. When she smelled that maple syrup scent, she would have known to pull over immediately, let the engine cool, and look for that crusty residue. She would have seen the failing hose, replaced it for $20, and been back on the road. Instead, many drivers ignore the smell until the dashboard lights up like a Christmas tree and steam starts pouring from the hood. By then the damage is done. As we move forward in this masterclass, we have covered the physical fluids and the thermal management. But there is a force inside your vehicle that is even more elusive and often more frustrating for the beginner. It is the invisible flow of electrons. In 2026, your car is essentially a high-powered computer on wheels. From the battery that provides the initial surge of life to the alternator that keeps the lights on and the sensors that monitor every breath the engine takes, the electrical system is the ghost in the machine. Do you know why a low battery can cause your transmission to shift poorly? Or why a single corroded ground wire can make your car act like it is possessed? We are about to move from the mechanical to the digital and electrical. Most people are terrified of wires, but once you understand the 3 basic laws of automotive electricity, you will be able to solve problems that leave even some professional technicians scratching their heads. We are going to teach you how to use a multimeter to see the invisible, and how to track down the parasitic draws that are draining your battery overnight. Are you ready to master the spark that brings the steel to life? The world of automotive electronics is next. The invisible flow of electrons is the nervous system of your vehicle, and in 2026 it is more complex than ever before. Many beginners are intimidated by wiring because, unlike a leaking radiator or a grinding brake pad, you cannot see electricity. You cannot hear a bad sensor or smell a voltage drop unless things have gone catastrophically wrong. To master automotive electronics, you must stop thinking of it as magic and start thinking of it as plumbing. Electrons flow through wires much like water flows through pipes. Voltage is the pressure, amperage is the volume of flow, and resistance is the size of the pipe. If you understand these 3 variables, you can diagnose almost any electrical issue in a modern vehicle. Imagine a driver named Robert in Seattle in the winter of 2026. Robert owns a 2022 crossover that has been remarkably reliable until recently. Lately, on cold mornings, the infotainment screen flickers, the power steering feels slightly heavy for the first 30 seconds of driving, and occasionally the car takes an extra second to crank. Robert's first instinct is to worry about the expensive electronic steering rack or a failing head unit. However, historical trends in automotive diagnostics suggest that over 60% of intermittent electronic glitches are caused by a failing battery or a corroded ground connection. In 2026, vehicles are packed with dozens of electronic control units that are extremely sensitive to voltage. If the voltage drops even slightly below 12 volts during the cranking cycle, these computers can brown out, leading to a cascade of ghost codes and strange behavior that has nothing to do with the actual hardware. The first tool in your electronic arsenal is the digital multimeter. This device allows you to see the invisible. A professional-grade multimeter can measure DC voltage, amperage, and resistance with high precision. To use it, you must first understand the state of your battery. A common misconception is that a 12-volt battery is actually 12 volts. In reality, a fully charged lead-acid or absorbent glass mat battery should read 12.6 volts when the engine is off. If your meter reads 12.0 volts, your battery is actually at a nearly 50% state of charge. If it reads 10.5 volts, one of the internal cells has likely shorted out. When Robert tests his battery in 2026, he finds it at 12.4 volts. That seems healthy, but voltage alone does not tell the whole story. He needs to test the cold cranking amps. This is the battery's ability to deliver a massive surge of current to the starter motor in freezing temperatures. In 2026, many modern cars use stop-start technology, which requires an AGM battery. These batteries are designed for deep cycling and high current delivery. If you replace an AGM battery with the cheaper flooded lead-acid battery, the potential outcome is a battery that fails within 6 months because it cannot handle the rapid charging and discharging cycles of a modern hybrid or stop-start system. Next, we must look at the alternator, the onboard power plant. While the engine is running, the alternator should be pushing between 13.5 and 14.7 volts. This higher voltage is necessary to overcome the internal resistance of the battery and recharge it while simultaneously powering the headlights, seat heaters, and navigation systems. A case study in alternator failure often involves a bridge of diodes. These diodes convert the alternating current produced by the alternator into the direct current used by the car. If a diode fails, it can allow AC ripple into the system. This is essentially electronic noise that can confuse the crankshaft position sensor or the transmission controller, leading to stalls or erratic shifting. By switching your multimeter to the AC voltage setting while the car is running, you can detect this ripple. Anything over 0.5 volts AC is a sign that your alternator is dying and needs to be replaced before it fries your sensitive electronics. One of the most elusive problems for a beginner is the parasitic draw. Imagine if Robert's car is perfectly fine during the day, but after sitting overnight, the battery is completely dead. Something is awake when it should be sleeping. In 2026, vehicles have a sleep mode, where the computers shut down most functions to save power. This usually happens 20 to 30 minutes after the ignition is turned off. To find the thief, you use your multimeter to perform a fuse voltage drop test. Instead of pulling fuses, which can accidentally wake up a computer and ruin your test, you measure the tiny millivolt level drop across the top of each fuse. This tells you exactly how many milliamps are flowing through that specific circuit. If the circuit for the interior lights shows a draw, you might find a stuck vanity mirror switch or a faulty door latch sensor that is keeping the system awake. The foundation of every electrical circuit is the ground. In a car, the entire metal chassis acts as the return path for electricity. This saves miles of wiring, but it creates a single point of failure: corrosion. Robert's car in Seattle is exposed to constant moisture and road salt. Over time, the heavy gauge wire that connects the battery's negative terminal to the engine block can develop a layer of green oxidation called verdigrease. This oxidation increases resistance. When Robert tries to start his car, the electricity can't find its way back to the battery easily, so the starter motor spins slowly. By performing a voltage drop test on the ground circuit, measuring the voltage between the battery post and the engine block while cranking, Robert can see if he is losing more than 0.2 volts. If he is, the fix isn't a new starter. It is simply cleaning a 10-cent metal contact point with the wire brush. As we look toward the future of your journey, we see that the electrical system is what bridges the gap between the mechanical parts we have already discussed. It controls the fuel injectors we will study later and monitors the oxygen levels in the exhaust. But before we get to the advanced sensors, we have to talk about how all this power and fluid actually makes it to the pavement. Your engine could be running perfectly, and your electronics could be flawless, but if your connection to the road is compromised, you are in a high-risk situation. We are about to transition from the engine bay to the corners of the vehicle. We are talking about the suspension, the steering, and the rubber that determines whether you stay on the road or slide off it. Do you know how to read the secret language written on the sidewall of your tires? Or why a vibration at 60 miles per hour might have nothing to do with your wheels? We are going to look at the physics of handling and the critical components that keep your car pointed in the right direction. If you think a tire is just a circle of rubber, you are missing half the story of automotive safety. The masterclass is moving to the chassis, where we explore the bridge between the machine and the earth. Are you ready to dive into the world of alignment, shocks, and the critical importance of contact patches? The next part of your journey starts at the ground level. Every single maneuver your vehicle makes, from a high-speed lane change on a rain-slicked interstate to a controlled stop at a suburban intersection, depends entirely on 4 patches of rubber no larger than the palm of your hand. This is the contact patch. In the year 2026, the technology embedded in your tires has reached a pinnacle of chemical engineering, but the physics of the chassis remains unyielding. To master auto repair, you must understand that the suspension and steering systems are not just about comfort. They are a complex mechanical computer designed to keep those 4 patches of rubber flat against the earth at all times. If a single component in this chain fails, the mechanical grip of the car is compromised, leading to potential outcomes that range from accelerated tire wear to a complete loss of directional control. Imagine a driver named Michael living in Denver, Colorado, in 2026. Michael drives a 2020 all-wheel drive crossover. Recently, he noticed a subtle rhythmic vibration through the steering wheel that only appears when he reaches 65 miles per hour on the highway. To most drivers, this is a minor annoyance. To a masterclass student, this is a diagnostic data point. Michael's first instinct might be to assume the wheels are out of balance, and historical trends suggest he would be right 60% of the time. However, Michael decides to perform a visual and tactile inspection of his tires first. He looks at the tread and notices a pattern called cupping: smooth, scooped-out dips across the surface of the rubber. This is not a balance issue. This is a suspension failure. Specifically, it is a sign that his shock absorbers are no longer controlling the vertical oscillation of the wheel, allowing the tire to literally dribble like a basketball down the highway. Before we fix Michael's suspension, we must learn the language of the tire itself. In 2026, the sidewall of a tire is a roadmap of data. You will see a string of characters like 245/45 or 1998W. The 245 is the width in millimeters. The 45 is the aspect ratio, meaning the sidewall height is 45% of the width. The R stands for radial construction, and 19 is the wheel diameter. But for a beginner, the most critical piece of data is the DOT code. Look for a 4-digit number at the end of the DOT string. If it reads 1221, that tire was manufactured in the 12th week of 2021. In 2026, that tire is 5 years old. Historical trends in rubber degradation show that even if a tire has plenty of tread left, the chemical bonds in the rubber begin to harden and crack after 5 to 6 years. This is known as dry rot. A hardened tire cannot grip the road in the cold, and it is prone to catastrophic sidewall failure. Case studies of high-speed blowouts often reveal tires that looked brand new but were over 8 years old. Now, let us look at the skeleton of the vehicle, the suspension. The most common modern setup is the McPherson strut. This unit combines a coil spring and a shock absorber into one assembly. The spring supports the weight of the vehicle, while the shock absorber or strut uses hydraulic valving to turn the kinetic energy of a bump into heat. To test these, you perform the bounce test. Walk to a corner of your car and push down with all your weight, then let go. The car should rise and stop. If it continues to bounce even once, the internal seals of the strut have failed. In 2026, a single high-quality strut for Michael's crossover costs about $180. A shop would charge him $400 in labor to install a pair. By learning to use a spring compressor safely, a tool that requires immense respect because it holds enough potential energy to be lethal if mishandled, Michael can save nearly half a month's rent in a single Saturday. Connecting the suspension to the steering rack are the tie rods. These are the literal arms that reach out and turn the wheels. There are inner tie rods and outer tie rods, connected by a ball and socket joint protected by a rubber boot. If that boot tears, road salt and grit enter the joint, grinding it down until it has play. To check this, you use the 3 and 9 test. With the car safely on jack stands, grab the tire at the 3 o'clock and 9 o'clock positions and try to wiggle it side to side. Any clicking or movement indicates a failing tie rod. If you do the same at the 12 and 6 positions and feel movement, you are likely looking at a failing wheel bearing or a ball joint. These components are the pivot points of your steering. In a 2026 case study of steering failures, neglected ball joints were found to be a leading cause of the wheel physically detaching from the lower control arm, a situation that is impossible to recover from at speed. Finally, we must discuss the geometry of the hunt, the alignment. There are 3 primary angles: camber, caster, and toe. Camber is the inward or outward tilt of the tire when viewed from the front. If the top of the tire tilts in, that is negative camber. Toe is the most critical for tire life. It is whether the tires are pointed toward each other like someone who is pigeon-toed. In 2026, many vehicles are equipped with advanced driver assistance systems, or ADAS. These systems use cameras and radar to keep you in your lane. If your mechanical alignment is out by even a fraction of a degree, your car's computer may struggle to calibrate the steering angle sensor, leading to erratic lane keep assist behavior. You might think the software is glitching when, in reality, your front left tire is pointed 3 millimeters too far to the left. By performing his own inspections, Michael discovers that his vibration was caused by a worn-out lower ball joint and a blown strut. He replaces them for $300 in parts. He then takes the car for a professional alignment, one of the few jobs a beginner cannot do at home without specialized laser equipment, and ensures his ADAS system is recalibrated. The potential outcome is a vehicle that feels factory new, tracks straight as an arrow, and preserves his expensive 2026 grade tires for another 40,000 miles. But all the handling and grip in the world are useless if you cannot dissipate the massive amounts of kinetic energy your vehicle carries at speed. You have mastered how to make the car go and how to keep it on the road, but now we must master how to make it stop. The braking system is a masterclass in hydraulics and friction, where temperatures can soar to over 1,000 degrees Fahrenheit in a matter of seconds. Do you know why your brakes might squeal even if the pads are new? Or why a pulsing sensation in the pedal is almost never caused by a warped rotor? We are about to move from the suspension to the most critical safety system ever invented. We are going to deconstruct the disc brake system, learn how to bleed air out of an ABS module without a scan tool, and discover the hidden reason why your brake fluid is the most neglected chemical in your garage. Are you ready to take control of the force that stops 4,000 pounds of moving steel? The art of the brake job is the next hurdle in your journey to total automotive autonomy. To understand the absolute gravity of the braking system, you must first understand the conversion of energy. When you are traveling at 60 miles per hour in a 4,000-pound vehicle, you possess a massive amount of kinetic energy. To bring that vehicle to a dead stop, that energy cannot simply disappear. According to the laws of physics, it must be transformed. Your brakes are essentially a thermal energy converter. They take the motion of your vehicle and turn it into heat through friction. Imagine a driver named Emily in the year 2026, commuting through the dense traffic of Los Angeles. In a single hour of stop-and-go driving, Emily's brake rotors may reach temperatures exceeding 500 degrees Fahrenheit. This is normal operating procedure for a modern car, but it illustrates why the components in this system are engineered to such extreme tolerances. If those components fail to manage that heat, the potential outcome is a phenomenon known as brake fade, where the fluid boils and the pedal goes straight to the floor, leaving the driver with no way to scrub off speed. The heart of the braking system is the hydraulic circuit, governed by Pascal's law. This law states that pressure exerted anywhere in a confined incompressible fluid is transmitted equally in all directions. When Emily presses her brake pedal, she is pushing a piston inside the master cylinder. This creates hydraulic pressure that travels through steel lines and rubber hoses to the four corners of the car. Because brake fluid is designed to be incompressible, that force is delivered instantly to the brake calipers. Inside the caliper, the hydraulic pressure pushes one or more pistons outward, forcing the brake pads against the spinning metal rotor. This is the moment of friction. Let us look at a case study involving Emily's 2022 compact SUV in 2026. She began hearing a high-pitched, metallic screeching every time she applied the brakes at low speeds. Many drivers ignore this, thinking it is just moisture or dust. In reality, this is a brilliant piece of mechanical engineering called the wear indicator or the squealer. It is a small metal tab attached to the brake pad. When the friction material wears down to a critical level, usually about 2 or 3 millimeters, the tab makes contact with the rotor, creating that audible warning. Historical trends in automotive maintenance suggest that catching a brake job at the squealer stage costs about 1/4 of what it costs if you wait until you hear a grinding noise. The grinding noise is metal-on-metal contact, meaning the friction material is gone and the steel backing plate is eating into the expensive cast iron rotor. To perform a masterclass brake inspection, you must look at more than just the pad thickness. You must look at the quality of the rotor surface. You are looking for heat checking, small radial cracks caused by extreme temperature cycles, and grooving. If you see deep circles in the rotor, it acts like a record player needle, wearing down your new pads prematurely. Furthermore, you must inspect the caliper slide pins. These pins allow the caliper to move back and forth so that it can apply even pressure to both the inner and outer pads. In a 2026 case study of uneven brake wear, over 40% of cases were caused by seized slide pins. When these pins are stuck due to dried-out grease or a torn rubber boot, one pad stays pressed against the rotor while the other does nothing. This leads to overheating, a pulling sensation in the steering wheel, and a significantly longer stopping distance. When Emily decides to tackle her own brake job in 2026, she follows a strict step-by-step protocol to ensure safety and performance. First, she loosens the lug nuts while the car is still on the ground, then lifts and supports the vehicle on jack stands as we mastered in Part 3. After removing the wheel, she uses a high-quality brake cleaner to remove the toxic carbon dust that has accumulated. A professional tip here is to never use compressed air to blow off brake dust. Historical trends in occupational safety show that even modern non-asbestos pads contain fibers that should not be inhaled. After removing the 2 caliper bolts, Emily does not let the caliper hang by its rubber hose. This is a common beginner mistake. A hanging caliper puts hundreds of pounds of stress on the internal crimps of the brake hose, which can cause an internal collapse that acts like a one-way valve, causing the brakes to drag. Instead, she uses a heavy-duty bungee cord or a dedicated caliper hanger to secure the unit to the coil spring. Before installing the new pads, Emily must address the caliper piston. Since the old pads were thin, the piston is currently extended far out of its bore. She uses a caliper compression tool or a large C-clamp to slowly push the piston back in. This forces the brake fluid back up the lines toward the master cylinder. In 2026, with complex ABS and stability control modules, some technicians prefer to open the bleeder valve during this process to prevent old, dirty fluid from being pushed backward through the sensitive valves of the ABS unit. The installation of the new pads requires precision lubrication. Emily applies a high-temperature silicone-based brake grease, only to the points where the metal backing plate of the pad touches the caliper bracket. She never, under any circumstances, allows grease to touch the friction surface of the pad or the face of the rotor. Contaminating the friction surface with grease can lead to a total loss of braking power on that wheel. She also cleans and re-greases the slide pins, ensuring they move freely with a light, springy action. Once the new pads and rotors are installed, the job is not finished. Emily must bed in the brakes. This is a specific procedure where the driver performs a series of controlled stops from 40 miles per hour down to 10 miles per hour without coming to a complete halt. This process uses heat to transfer a thin, even layer of friction material from the pad onto the surface of the rotor. Historical data shows that properly bedded brakes have a 20% higher stopping force and are much less likely to develop the pulsating vibration often mislabeled as warped rotors. In reality, rotors rarely warp. What people feel is an uneven buildup of pad material on the rotor face caused by getting the brakes very hot, and then sitting at a stoplight with the pads pressed firmly against the hot metal. By doing this work herself, Emily has transformed her vehicle's safety profile. She spent $150 on premium ceramic pads and coated rotors, whereas a local shop in 2026 would have charged her $550 for the same service using lower-quality house brand parts. More importantly, she knows exactly what is between her and the pavement. But there is a final mystery to solve. You have the spark, you have the fluids, and you have the stopping power. But for the engine to actually generate that kinetic energy, it has to breathe. Just like a human being, an engine requires a precise mixture of oxygen and fuel, and it must exhale the waste products of that combustion with zero restriction. If the lungs of your car are clogged or if the throat is constricted, your engine will struggle, gasp, and eventually fail. Do you know why a simple $20 air filter can be the difference between 20 miles per gallon and 30? Do you know how to diagnose a vacuum leak using nothing but a can of soapy water? Or why a clogged catalytic converter can make your car feel like it is towing a 10-ton trailer? We are about to move into the respiratory system of the machine. The intake, the fuel delivery, and the exhaust are the final pieces of the performance puzzle. Are you ready to optimize the breath of the beast? The science of air and fire is coming up next. To understand how an engine breathes, you must first conceptualize the internal combustion engine not as a complex metal box, but as a giant high-speed air pump. In the year 2026, the efficiency of this pump is dictated by a microscopic dance of sensors and actuators. Imagine a driver named Brandon in Austin, Texas. Brandon owns a 2021 turbocharged pickup truck that he uses for both his construction business and weekend trips. Lately, the truck has felt sluggish, as if it is struggling to pull a trailer that isn't there. When he merges onto the highway, the engine hesitates, and his fuel economy has dropped from 22 miles per gallon to 16. Brandon is facing a potential outcome where a dealership might recommend a full fuel system service and a turbocharger inspection, totaling over $2,000. However, the reality of Brandon's problem likely sits in the respiratory tract of his vehicle. Shutterstock. Explore. The first stage of the engine's breath is the intake system. It begins with the air filter. In 2026, air filters are more than just pleated paper. They are high-efficiency barriers designed to catch particles as small as 5 microns. If Brandon's air filter is clogged with Texas dust, the engine has to work harder to pull air in, creating a vacuum where there should be flow. This increases pumping losses. Historical trends in automotive data show that a severely restricted air filter can reduce power output by up to 10% in turbocharged engines, as the turbo has to spin faster to compensate for the lack of available air, leading to increased heat and wear. Once the air passes the filter, it encounters the mass airflow or MAF sensor. This is a delicate piece of electronics that uses a heated wire to measure the density and volume of the incoming air. As air passes over the wire, it cools it down, and the car's computer calculates how much current is needed to keep that wire at a constant temperature. This calculation tells the engine exactly how much fuel to inject. If a single drop of oil from an over-serviced performance filter or a speck of dust hits that wire, the readings become skewed. The engine might think it is receiving less air than it actually is, leading to a lean condition. Brandon can solve this with a $10 can of specialized MAF cleaner and 5 minutes of labor, potentially avoiding an expensive and unnecessary sensor replacement. Beyond the sensor lies the throttle body. In 2026, almost every vehicle uses electronic throttle control, or drive-by-wire. There is no physical cable connecting your foot to the engine. Instead, a motor opens a butterfly valve based on a signal from the pedal. Over time, carbon vapors from the engine's crankcase can settle on this valve, creating a sticky residue. This causes the valve to stumble or stick, leading to the erratic idle or hesitation Brandon is experiencing. A case study of modern engine maintenance reveals that cleaning the throttle body every 50,000 miles can prevent the limp mode errors that often terrify unsuspecting drivers. Now, we must discuss the chemistry of the explosion. To achieve perfect combustion, the engine aims for a stoichiometric ratio. This is a precise chemical balance where all the fuel is burned using all the available oxygen. For a gasoline engine, this ratio is approximately 14.7 to 1, meaning 14.7 parts of air for every 1 part of fuel. If the ratio falls to 12 to 1, the engine is running rich, too much fuel, leading to carbon buildup and wasted money. If it climbs to 17:1, it is running lean, too much air, which causes the combustion chamber temperatures to skyrocket, potentially melting spark plugs or burning exhaust valves. In 2026, the way fuel reaches this mixture has changed. Most vehicles now use gasoline direct injection or GDI. Unlike older port injection systems that sprayed fuel behind the intake valve, GDI sprays fuel directly into the combustion chamber at pressures exceeding 2000 psi. While this increases power, it creates a new problem: carbon buildup on the intake valves. In older engines, the gasoline acted as a solvent, washing the valves clean as it entered. In a GDI engine, the valves never see a drop of fuel. Historical trends in GDI engines show that by 60,000 miles, the intake ports can become so choked with carbon that the engine literally begins to suffocate. Brandon can mitigate this by using high-quality top-tier detergent gasoline and performing a specialized intake foam cleaning service, which chemically dissolves the carbon before it requires a $3,000 mechanical walnut blasting procedure. After the power stroke, the engine must exhale. The exhaust system is not just a tailpipe. It is a sophisticated laboratory. It starts with the oxygen sensors, which act as the nose of the vehicle. These sensors live in the exhaust manifold and tell the computer if the air-fuel ratio was correct. In 2026, these are wideband sensors that provide a constant stream of data, allowing the computer to make fuel trim adjustments hundreds of times per second. By using an OBD2 scanner to look at long-term fuel trim, Brandon can see if his computer is struggling. If the trim is at plus 20%, the computer is screaming that it has a massive air leak or a fuel delivery problem and is trying to compensate by dumping more fuel in. The most expensive part of the exhale is the catalytic converter. This device uses precious metals like platinum, palladium, and rhodium to trigger a chemical reaction that turns toxic carbon monoxide and hydrocarbons into harmless nitrogen, carbon dioxide, and water vapor. Catalytic converters do not usually die of old age. They are murdered by the engine. If Brandon's truck continues to run rich because of a dirty MAF sensor, that unburnt fuel will enter the converter and ignite, melting the ceramic honeycomb inside. This creates back pressure, which is like trying to run a marathon while breathing through a straw. A clogged converter will make a vehicle feel completely powerless and can even cause the engine to stall under load. Brandon's journey through the respiratory system of his truck leads him to a realization. Automotive repair in 2026 is about managing the flow. By replacing his air filter, cleaning his MAF sensor and throttle body, and using a fuel system cleaner designed for GDI engines, he restores the 14.7:1 balance. His pickup truck regains its lost horsepower, his fuel economy returns to factory specifications, and he avoids the high-stakes cost of major component replacement. He has successfully optimized the breath of the beast. But even with the engine breathing perfectly and the spark firing on time, there is one final frontier every beginner must conquer before they can call themselves a master of their own mobility. You have learned how the machine works, how to keep it cool, how to make it stop, and how to fuel its fire. However, the most successful repairs are not just about the work you do with your hands, they are about the strategy you use with your mind. How do you source parts in a world of supply chain fluctuations and counterfeit components? How do you organize your workflow so a 2-hour job doesn't turn into a 2-day disaster? And most importantly, how do you build a long-term maintenance roadmap that ensures your vehicle reaches 300,000 miles and beyond? We are reaching the finish line of this masterclass. The final part of our journey is about the philosophy of the master technician and the roadmap to automotive immortality. Are you ready to see the big picture and finalize your transformation? The ultimate guide to the long-term ownership strategy is next. Automotive immortality is not a matter of luck, it is a matter of strategy. In the year 2026, the gap between a vehicle that heads to the scrapyard at 100,000 miles and one that thrives at 300,000 miles is defined by the quality of the parts you source and the discipline of your workflow. Imagine a driver named Carlos in Miami. Carlos owns a 2019 hybrid sedan that he uses for rideshare services. By 2026, he has reached 250,000 miles. His secret is not a specialized mechanical degree, but a deep understanding of the tiered part strategy. Carlos knows that in the 2026 marketplace, the influx of counterfeit components has reached an all-time high. Historical trends show that nearly 15% of automotive sensors sold through major third-party online marketplaces are either substandard clones or outright fakes. If Carlos buys a $20 oxygen sensor instead of the $90 original equipment manufacturer or OEM part, the potential outcome is a sensor that reports incorrect data to the engine computer, leading to a lean running condition that eventually melts his catalytic converter. To master your own journey, you must learn where to spend and where to save. For non-critical components like cabin air filters, wiper blades, or plastic trim clips, aftermarket parts are often identical to OEM and provide significant savings. However, for the central nervous system of the car, sensors, ignition coils, and electronic actuators, you must stick to OEM or OES, which stands for Original Equipment Supplier. These are the companies like Bosch, Denso, or NGK that actually manufactured the part for the car company in the first place. In 2026, many of these manufacturers have implemented QR codes on their packaging that allow you to verify the authenticity of the part against a global database before you ever install it. This level of diligence is what ensures that a repair actually solves the problem, rather than introducing a new, more elusive variable. Beyond the parts, the master technician is defined by the organization of their environment. Imagine if you are in the middle of a complex valve cover gasket replacement. You have removed 22 different bolts of varying lengths and 3 different electrical brackets. If you simply throw these into a pile on your workbench, you have created a high-risk situation for cross-threading or using a bolt that is too long, which could punch through the cylinder head casting. A professional workflow involves the use of labeling and containment. In 2026, technicians use digital documentation. Before you remove a single bolt, you take a high-resolution photo or video of the area. You then use magnetic trays or even simple muffin tins to separate bolts by the component they belong to. You label each tray with masking tape. This systematic approach reduces the cognitive load of the repair. Instead of trying to remember where everything goes, you are simply following the reverse order of your own documented steps. The third pillar of the masterclass is the maintenance roadmap. In the United States, we often follow the 30-60-90 rule, which refers to major service intervals at 30,000, 60,000, and 90,000 miles. However, by 2026, many manufacturers have pushed these intervals further out to make the cost of ownership appear lower. This is a case study in planned obsolescence. A master of auto repair ignores the marketing and sticks to the physics of the machine. At the 60,000-mile mark, even if the manual says the transmission fluid is lifetime, a proactive technician performs a fluid analysis. You are looking for the presence of friction material and the smell of burnt additives. By 2026, simple home test kits allow you to send a small sample of your oil or transmission fluid to a lab that provides a spectroscopic analysis of the metal content in your fluid. If the lab reports high levels of copper or lead, you know your bearings are wearing prematurely, allowing you to adjust your driving habits or plan for a repair before it becomes a roadside emergency. We must also address the psychological aspect of auto repair. The diagnostic mindset. Many beginners fall victim to the parts canon, a term used when a person replaces part after part hoping to stumble upon the fix. In 2026, with the high cost of components, this is an expensive and ineffective strategy. The master technician follows a diagnostic tree. If the car won't start, you don't buy a battery, then a starter, then an ignition switch. Instead, you test the battery voltage first. If the voltage is 12.6, you check the signal wire to the starter. If the signal is there but the motor doesn't spin, only then do you replace the starter. This logical progression saves thousands of dollars over the life of the vehicle. Historical data from independent repair shops suggest that nearly 30% of return parts were never actually defective. They were simply the result of a poor diagnosis. As you stand in your garage at the end of this 10-part masterclass, you are no longer the person who looked at the dashboard light with fear. You have transformed into someone who understands that a vehicle is a predictable system of inputs and outputs. You have the tools to measure the electricity, the knowledge to manage the fluids, and the safety protocols to protect your life while doing it. You have seen how a simple $20 air filter or a 10-cent crush washer can be the difference between a car that lasts 10 years and one that lasts 30. You are now part of a growing movement of individuals reclaiming the right to repair, maintaining the mechanical heritage of the United States, and building a more sustainable future by keeping existing machines running at peak efficiency. But remember, this is only the foundation. You have mastered the external systems and the fundamental maintenance that keeps a car on the road. However, there is a deeper level of mechanical mastery that we haven't touched yet. What happens when the problem isn't a sensor or a fluid, but a mechanical failure deep inside the heart of the machine? What do you do when a timing belt snaps? Or when a head gasket fails and begins to mix your oil and coolant into a milky sludge? The world of internal engine repair and transmission rebuilding is a high-stakes arena where tolerances are measured in the thousandths of an inch, and a single mistake can result in the total destruction of the engine block. Are you ready to move from the driveway to the engine stand? Are you prepared to learn the art of precision measurement, the science of torque-to-yield fasteners, and the complex timing procedures that synchronize the valves and pistons in a high-performance engine? Our journey into the advanced masterclass, Internal Systems and Heavy Repair, is about to begin. We are going to go deeper than the surface, opening the very core of the internal combustion engine to reveal the secrets of peak performance and total mechanical restoration. The next level of your transformation is waiting under the valve cover.